The first lesson in our quest of mechanics Newton's laws of motion is the study of dynamics. In this lesson, I will share with you the basics of understanding Newton's laws of motion. Let's kickstart the lessons. So lesson 1 will be looking at dynamic concepts. So dynamic concepts really, they are the concepts that study what causes an object to move. So when we talk about dynamic concepts, we're looking at concepts that help us to understand why objects are able to move, what causes them to move, right? The first dynamic concept that we're going to look at is called a force. In its simplest form, we can define a force as a pull or a push, right? So imagine here in our diagram figure 1.1, if you look at diagram A here, we have here a shopping cart that is being pushed by a force F, right? And the shopping cart moves to the right as it's pointing in that direction of the right. It moves to the right because there is some pushing that is exerted here. We call this a force, right? Now, a force is a vector quantity, right? So now the question would be, what is a vector quantity, right? A vector quantity is a physical quantity that has both the magnitude, and direction. Now, what do we mean by magnitude? Magnitude means size, right? So by that we mean how big is the force that we're applying here, right? How big is the force? So the way we represent vectors is that we use an arrow like this and an arrowhead here. Now the length of this arrow here, right? The length of the arrow here represents the magnitude, represents the size of the force. Now, if I were to have a long arrow like that, it means it has a bigger magnitude compared to this one. So that's how we represent vectors. But also vectors have a direction really. So if now you say here, this is pointing to the right here, that's the direction of our vector. So a force has that nature that you can you can really look at it from studying its magnitude, its size, and also direction. Now the symbol for the force is generally the letter F. We use the letter F to represent or denote the force. There are cases where we use other letters, right? But generally we use the letter F, right? And then the SI unit of the force is measured in newtons, right? We use the capital letter N to represent that SI unit. So this is to say that if I say here, I'm pushing a cart with a force of 5 Newton to the right, that's how you would fully write the force. To say my force is F is equals to 5 Newton. What is this? This is the magnitude. The magnitude always has the SI unit, right? Then the second part to it will be the direction, right? So I've used the symbol, I've used the SI unit, and I've put magnitude on it because it's a vector quantity. It has the magnitude. So that's how you will write your force. Now there are two ways in which we represent the force. One of the ways is by a force diagram. Now if you look at our diagram A again here, you'll find that this type of a diagram is called a force diagram because the way we define a force diagram is that it's a diagram that shows all the forces acting on an object and the picture of the object. Now this picture can be a schematic diagram, even here it's not really a picture but it's a schematic. We can see here that this thing is like a shopping cart, right? So this type of a diagram, we call it a force diagram, right? Another way in which we represent a force is through a free body diagram, right? Now a free body diagram really is defined in the same way as the force diagram, right? It's a diagram that shows all the forces acting on an object. The only difference is that with a free body diagram, we do not have the shape or the picture of the diagram. We do not have the shape or the picture of the diagram. So what we do here is that we represent the diagram as a dot. We model this shopping cart, right, and change it to a dot, because the shape is not really important here when we want to look at the forces acting on the object, right? And we then draw our vector as it is on that dot. It's going to the right and it has that length, that magnitude. Now this diagram, it becomes a very simplified diagram in helping us to solve problems, right? We'll see when we go on with our lessons and we get to a point where we draw this and solve problems, right? So that is just the basics in understanding our first dynamic concept, a concept that helps us to understand what causes object to move, right? If there's any movement in those objects. Another important concept that I need us to learn is called the net force, right? The net force is defined as the vector sum of all forces acting on an object. All right, so if you have an object and there's a number of forces acting on that object, we call adding all those forces, they will give you the vector sum. Now I want to just break this down for you. If you see the word sum in mathematics, it means that is a number that you obtain after addition. So for instance, if you say 2 plus 3, the answer is 5. Normally they'll say the sum of 2 and 3 is 5. That's how we'll say it. The sum of 2 and 3 is 5. Meaning, if you add 2 and 3, you get a 5. So the same concept or the same logic is used when we define the net force here to say, look, if you add the first force, F1, and you add the second force, F2, and you continue adding other forces here until you get to the nth force, the answer that you should get will be called the net force, and it's represented by a symbol F and a superscript net at the bottom there, right? So this will mean the net force. Again, you'll see that this is a force, right? F1, F2 up to nth term, they're measured in newtons. So the net force also would be measured in newtons because you're just adding, right, quantities that are of the same nature, right? So now you will get them in newtons, right? Now this equation, I want to talk about something about it. Some people like to, use a symbol for the net force that says sigma F, right, to represent the net force. Now this symbol here means sum, right? It's another letter that we have in mathematics that means sum. It tells us that we are adding forces, right? So you can use that if you like. It's a very simple notation to use, and sometimes it's convenient on solving certain problems, than using FNet. And sometimes the net force is called the resultant force, right? And is then given the symbol FR, right? Some people like to use this, so you can say FR is equals to F1 plus F2 up until Fn, right? Newton, when he was studying these things, these forces and all that, especially when he stated his first law originally back in the day, during his times, he called this force unbalanced force. If you think about it, it's the word unbalanced force. I'm just trying to bring this to emphasize the point of what we're doing here. The word unbalanced force speaks to the fact that the net force is the sum, is a number that you get after adding these forces. You'll see that some of these forces will be negative here depending on their direction, some will be positive, and then the answer that you get won't be balanced, right? It will be either bigger than this one here, right, or it will be smaller, right? So that's the idea, right? At this stage now, I think we can do a problem where we try to apply the knowledge that we have learned in this lesson to close up this lesson. We'll close it up with a problem. Remember that what we said that if we come across problems, the mindset that we have is that of I can solve this problem, right? this we said is our academic constitution, right guys? If you want to know more about this academic constitution, please go to a separate video that we have done that speaks about the academic constitution. I break down, right? It's a video that tells you how you should approach and solve exam questions or problems, right? It makes these problems to be easy if you follow it. Go there to get the details of this academic constitution. Now, the first thing of the on our academic constitution really is to say, look, let's interpret the problem, right? Interpreting the problem involves reading the problem, right? Choosing direction, right? Putting our data down, right? And also make sense of our problem, right? If there is no sketch, draw it, but here I can see we have the sketch, right? Then we'll move to the next step of C, which involves classification. But let's first start with interpretation. So interpretation is, let's start with reading the question. Now I'm going to read the question now. The question says, look, two forces are exerted against a wall with magnitudes 34 Newton and 60 Newton to the right? If you look at this diagram, you'll see that 34 is less than 60. And if you look at these two vectors here, F1 and F2, you would see that F1 is smaller to F2. That means now this is 34 Newton and this is 60 Newton here, right? And again, I think I'll then also start coming to, breaking down my question, so that now we can say, we choose direction and say, look, take right as positive. So this means anything that goes to the right here on our problem, anything that goes to the right on our problem would be positive, right? Anything that goes to the right on our problem would be positive, right? And then now, because I've chosen direction, I can really quickly write down my data to say I have F1. We have identified that to be 34 Newton. It's positive because it's going to the right. We also have 60 Newton, which is positive also because it's going to the right. Now let's continue. The problem says the third force pushes the wall to the left at 150 Newton is shown. Look at this. There's a force that goes in that direction. So this means F3 is going to be 150 Newton, but it has to be negative because it doesn't go to the right. It doesn't go to the right. It actually goes to the opposite direction. It goes to the left. So F3 is equals to negative 150 Newton. Right. Now at this stage now we have interpreted our problem, right? We have interpreted our problem. So we have interpreted our problem here, right? We go to problem classification now. Our problem classification says which part of our theory, our laws and concepts, or even formulae relate. Where can we connect this information to right? Which formulas can we connect this to, right? I look at this problem as a problem that involves a number of forces acting on an object, right? The wall in this case. So this could be a problem where they ask us about the net force, maybe define the net force as a theory question, right? Or maybe calculate the net force. They can ask us maybe to draw a free body diagram, because already they've given us in this problem they've given us the force diagram. Maybe they can say draw a free body diagram, right? That's how you connect or classify this problem, right? And there could be other theories like define a force, maybe, just to check your understanding if you understand what a force is. Now so now we have classified this question. We move into the next part, which says answer the problem. We are ready to answer the problem now. So now we go to the actual questions to answer the question. This is 1.1. So the first question says, what is the name of the diagram above? I mean, I think I've said this as I was explaining that, look, this diagram here is the force diagram because it's a diagram that shows all forces acting on an object and the picture of the object, a schematic diagram of the object, right? Simple, straightforward. And again, if you look at this question, it's worth 1 mark. It's worth 1 mark. if you look at this question, is worth 1 mark. So here they'll give you 1 mark for that. Now, the second question, 1.2, says draw a free body diagram of the forces acting on an object. I mean, as part of our classification, we expected this question. We are going to change the wall into a dot when we draw a free body diagram, right? Such that now F1 will go in that direction. This will be F1, and again F2 will go in that direction. This will be F2. Now notice that these two forces, how I've drawn them, they are not the same in length, because we know that F1 is 34 and F2 is 60, right? Again, I'm not drawing these things using a scale, but at least you have to distinguish them to say they're not the same. It will be wrong for you to say these forces are like this, because they're not equal. You know, even if your line ended up here, that's fine. Because you're not using scale, we can see that they are not the same, right? If you draw something like this, it will be wrong, because I mean F2 is not smaller than F1, right? Then we draw the next force, which tends to be bigger than the 2, right? F3. And again, you know, as part of our interpretation, you can see that if I add these two forces here, this side, since they're going in the same direction, this one's here 60 plus 34, they give me roughly 94, I think, right, which is much smaller than this 150. So already we can see that, you know, this one force, this single force is much larger to these two forces. Very important to observe such things when you solve a problem, because you know it might assist you later on to judge, to navigate your problem, to see if you're in the right path, right? Now another thing that I wanted to talk about was around the marking. Here is 3 marks. So these 3 marks emanates, or it comes from the fact that you have 3 arrows there, right? And your arrows are straight, you have used a ruler and all that. Very, very, very important, and simple things to actually master and get the mark here. I usually say these are free marks, right? Now question 1.3 says calculate the net force exerted on the wall. I mean, we expected this question, right, when we did our problem classification. So now this would mean we'll use the formula F net is equals to F1 plus F2 plus F3. Notice that N here is equals to 3, because you only have 3 forces. Will end at the third force, right? Now here we'll then substitute our forces. We'll say F1 is 34 plus 60 plus, and then here we'll have minus 150, because it goes in the opposite direction. Now at this stage we can pull our calculator and say 34 plus 60 plus minus 150, right? That should give you negative 56 newtons. Now what does this answer mean? It means that the net force is equals to 56 newton. Remember that the direction here, the negative here, I meant to say, represents the direction. So this here would mean we're going to the left, since we chose the right to be positive, right? So we're going to the left, right? Then really at this stage we are done with our problem. I just want to show you that it's 3 marks, that it comes from the formula, the correct substitution for everything here, and they give you 1 mark for the final answer. Look at my final answer now. Already I'm doing navigation. Already I'm doing navigation here by checking also my answer, because we are here, right? Already I'm doing navigation to say, does my answer make sense? Well, it doesn't make sense, because I said here 56 what? Apples, bananas, you know? So this has to be newtons, right? 56 newtons to the right. Now this looks like an answer that makes sense, but we can go further to look at it. We expected a value that will go in the opposite direction, right? We expected the net force to go in the opposite direction. As I was saying last time here, that if you add these two forces, they give you 90, and here you have 150, which is negative. So obviously we expect a force that will go in that direction, right? I just want to draw it here. We expect a force that will go in that direction. Look at my vector, so bad. We expect a vector that will go in that direction as the net force. Now, what does the net force actually mean? So if you look at these forces here, they're acting on this object. So the net force means that you know, if I were to draw this force, it will be negative 56 in the negative direction, the net force. So it means that these three forces, right, F1, F2, and F3, they have the same effect as this one single force. So this means that if the wall was to be pushed by this one force, right, of negative 56 Newton, meaning if somebody was to push the wall with a force of with a force of 56 Newton to the left, because it's negative, it will be the same as pushing this wall with this force of F1, F2, and this force of F3 simultaneously. So it has the same effect. It has the equivalent effect, right? If the wall were to collapse, right, when you push it with these three forces, it will also collapse if you push it with this single force. But the net force is very interesting because it also gives us a hint of which direction will the wall fall. If it were to collapse, it will fall in this direction. It will fall towards the left because the net force is directed towards the left, right? The net force is directed towards the left, so the effect will be the same, right? Even if it doesn't fall, right, but the effect is that the net force will, so these three forces are producing an effect that goes to that. That's what the net force means, and that's what we need to calculate the net force. It becomes a very important dynamic concept in explaining a motion. You know, in this case I was saying if the wall falls, it can assist us to understand why the wall fell to the left instead of the right. So now we looked at how we got our 3 marks there, right? And so that's part of navigation, making sense of our answer, right? Making sense of our answer. Of course, in this case, I don't know if the wall will fall, but I was just giving you an example in terms of the observed effect. Remember, we said on our academic constitution in the previous video that I was talking about that where we look at the academic constitution, that we're dealing with physical sciences. We use our 5 senses. We have to observe, taste, smell, and all those 5 senses that we discussed. Now, the other thing that we need to do in terms of navigation is to see that what happens, right, to the net force. What happens to the net force, to this answer that we have, if we were to change any one of these parameters, right? On this equation, you would see, or it should make sense to you, that if I increase this force, I make it bigger, the net force should also be bigger. If I change this force, I make it bigger, the net force should be bigger as well. If I change this one, I make it bigger, the net force we expect as well to be bigger, and the vice versa, right? So if you were to decrease any of these forces, we expect also the net force to decrease, because this is just a simple addition equation, right? Now this one I'll do it through answering the question. As I said, that examiners sometimes like to bring this question, like to give you this question. They like to give you this part of navigation as a question, because if you look at this one, the statement goes by all the forces are now halved. Look at what they do. They're changing some of their variables. They're changing these variables here, right? And then they ask you there at 1.4, how will the net force change? And then if we change these variables, how will the net force change, right? Doing this will help us to judge if our answer is correct or not, because we expect that if you increase this or decrease this, this should also increase or decrease, right? So here we have halved all these forces. We expect this force also to be halved, right? Now we will do it in a form of a calculation to see if that really is true. So now here we're saying that the net force is equals to F1 plus F2 plus F3. Now you'll realize that now what we said now here is that this force now is halved. It means it's going to be 30. This one also would be 17 because it's halved. And this one here, half of 150, I think this will be 75 Newton. Now you realize that the direction hasn't changed according to our problem. They haven't said anything about direction. Direction hasn't been changed, so we still have the same direction. So this means here we still have a negative, right? Because it didn't change direction, it only changed its magnitude, right? Now we come this side to then solve the problem to say now here we have 17 plus 30, and then we have plus minus 75, right? Then what net force do we get now, right? So here we have 17 plus 30 plus this says we have a negative 28 newtons. Immediately I can see that at least we're going to this right direction, because here our direction hasn't changed. We expect the net force to still go in the direction to the left, right? So this would be 28 newton to the left. But now, very important, is this new force, is this new net force half of this previous net force? Is it half of it, right? So now we can quickly check that. That's where we check if our answer is correct. To say 56 divide by 2, or you can multiply it by 0.5, or you can divide it by you can multiply by 1 over 2, right? It gives you the 28 there, right? So this is indeed half the force, right? So you can see that by halving all these forces, we also halve the net force, right? And that's how we know that our problem is right. And that's why they ask you these questions, guys, in your exams, because they're teaching you to judge, to see if your answer is correct, if there's any errors, right? And that is the first step of our academic constitution, as thoroughly discussed in our video where we discuss the academic constitution. And this is a very, very important tool for all grades, right? Grade 10, 11, and 12. So be sure to adapt the academic constitution. I can solve this problem. So here it means our answer will be halved. We'll choose halved. Our net force must be halved. And that's how you solve those problems, ladies and gentlemen. Thank you for staying with me up until the end of this lesson. If you like this content and you want to see more of this content, please give me a thumbs up, put your comments in there. If there's anything you didn't understand, please put there in the comment section. I will respond to it, or send me a direct email at thescienceless@outlook.com.